Okay, very good. Welcome everyone, both people who are here and people who are online. I hope the online people can hear well. Someone can unmute and tell us if you can hear.
Yeah, it is audible, sir.
Okay, very good. Okay, so it's a pleasure to welcome Abhijit Gadde, who I've known for many years. He did his PhD in Stony Brook, like many eminent people, including Rohini Godbole, Ashok Sen, and less eminent people also, like myself. And then he went to Caltech for postdoc. Was that in the math department of Caltech? Or
theoretical physics.
Theoretical physics. But it was a very mathematical project that I remember you working on.
Yes.
It was some new formulae which had just appeared in mathematics and in the mathematics literature. And I think by someone in Caltech or something like that. You had some interface with people there.
Yeah, I worked with Sergei Gukov, who works on an interface of physics and mathematics.
Then after that, he went to IIS Princeton for a second postdoc, and I think from there came to TIFR as a faculty member, where he now is. And he'll be giving 3 lectures. So today there'll be 2, one now, one at 3 p.m. And the last one is on Monday at, I don't remember, but please check the...
3 p.m.
Okay, 3 p.m. And those who are not subscribed to this mailing list should please subscribe. There will be some instructions on that. I think Manish knows if you want to ask. Yes. Okay. So with that, let's start.
Okay. Thank you very much for this kind introduction. So I have been asked by the organizers to give a set of lectures and make it accessible to someone who is trained as a mathematician, advanced undergraduate and early graduate students. So I've decided to talk about conformal and superconformal representation theory, given that this series is mainly about representation theory. And this is something that physicists nowadays care deeply about. No, not just nowadays, but even earlier. So let me just let me just present first of all the plan of the lectures. So as Sunil said, there will be 3 lectures. So in the first lecture, I basically plan to give some quick and dirty introduction to quantum field theory from the point of view of path integrals, starting with finite dimensional path integrals, focusing on their symmetries. And as I go along, I will introduce some elements that are near and dear to physicists and how we like to think about certain types of integrals, because that's what they will be at the end of the day. They'll be infinite dimensional integrals, but integrals nonetheless. And then I will get into this very specific type of symmetry called conformal symmetry. This is not, for a physicist, one would want to have some motivation to study such symmetries. And such symmetries indeed play an important role in describing physics of various systems near what is called their critical point. And these symmetries are quite powerful. So that's why we study these symmetries and their action on the Hilbert space. And naturally, they are introduced to their conformal representation theory. And then in modern physics, one also talks about supersymmetry. These are different types of symmetries compared to the ordinary ones. And in the last lecture, I will marry supersymmetry and conformal symmetry together and talk about superconformal symmetry and study its representations. Okay. Now, these representations can be studied from various points of view, because we are interested mainly in unitary representations. And it will depend on what I mean by unitary. What is the hermiticity condition on the Lie algebra? What is the real form, in other words? And that will guide us to look at unitary representations. Okay, so let me just begin with some general words of motivation. So in physics, symmetries play an important role, because you expect physical laws to be invariant under various transformations. For example, if you do an experiment here or you do an experiment somewhere else, you should get the same answer. So there should be a symmetry of physical laws which lets you translate your system in any direction. And this symmetry is called the translational symmetry. And by their very nature, these symmetries form a group, because if you translate it in one direction and expect an invariance, and translate in another direction and expect an invariance, then a composite operation of translating in both directions, you expect again an invariance. So clearly, such symmetries, they form a group. Now these groups could be either continuous groups or discrete groups. So this example that I gave of translation is a continuous group. Another type of invariance that you expect from physical laws is that even if you rotate your experimental system, you should get the same answer. So there should be some rotational symmetry that we expect for physical laws. So these symmetries are continuous symmetries. So one is familiar. So in mathematics, you would call them Lie groups. Symmetries, the groups associated with the symmetries would be Lie groups. But in addition to Lie groups or continuous symmetries, there would also be discrete symmetries. So for example, sometimes you may want your physical laws to be invariant under mirror reflection. So whatever happens here, in the mirror reflection also you expect similar things to happen. You may or may not demand that, but that's something that physical laws, I mean, that you can demand. But this symmetry is a Z2 symmetry. It's a discrete symmetry. So the main point of telling you this is that symmetries are very natural in physics. They could be continuous or discrete, and they form a group. Okay, and in quantum mechanics, we also have vector spaces. The vector spaces are just as ubiquitous as groups. So because in the quantum mechanics, state of a system is described by a vector. So in particular, you can multiply the state by a complex number and add them. So these are vector spaces over C. So you can multiply them by complex numbers and add them together, which is something that you cannot imagine in classical mechanics. In ordinary classical mechanics that we learn in school, you cannot imagine adding a configuration of particle. A configuration of particle is here and here together, and describing the state as particle here plus particle there. So this is not something that you can add. But in quantum mechanics, let's just precisely do that. And that's what results in various types of interesting interference patterns or entanglement effects and so on. So you are familiar with the Schrodinger cat, whether it's dead and alive, it can be together because the state of the system can be sum of the states. So in that sense, vector spaces are very ubiquitous. That's the point of me telling you this. And you have symmetries and you have vector spaces. So it's only natural to talk about representations. Okay, so this symmetry group will act linearly on this vector spaces, and we will study its representations. Now, why particular this symmetry, conformal symmetry or superconformal symmetry? There are various types of symmetries. As I mentioned, there's translations, and then there's rotations. Of course, one can talk about symmetries and the representations associated with that. And we do, for example, in three-dimensional space, the rotational symmetry is nothing but the Lie group SO3, 3x3 matrices with determinant 1. And we do talk about such things, and we talk about the representations. They are given by various spins, finite dimensional representations. But conformal symmetries are special. So conformal symmetry consists of this translational symmetry, rotational symmetry. But in addition to that, there are certain other symmetries, such as scale symmetry and what is called the special conformal symmetry, which we will talk about in more detail as we go along. And so let me just start writing a few things. So there are translations, rotations, plus you can have scale symmetry. Okay, so this translations meaning if you have some space, let's say labeled by some coordinate x, and this is, you should think of this as the space in which we are doing physics. Okay, so I will tell you where exactly all this fits, but let's call this a vector x mu, and if x mu goes to x mu plus a mu, that's what we call the translation, because we just move the coordinate by a certain amount, fixed amount, by a mu, this vector a mu. So this mu is an index, okay, which takes values from 1 to d. Okay, so physicists like to keep this indices very explicit. So rather than just thinking of x as some vector like this, you emphasize its coordinates given by this label mu. So you have x1, x2, x3, x4, xd. So this would be the rotation, and similarly, this would be the translation. And if you have x mu going to some r mu nu, x mu, where this is some matrix, D by D matrix, with the determinant 1, orthogonal matrix with determinant 1. So this is the special orthogonal transformations. This would be the rotation. This is what we are familiar with when we say rotations in physical space. So in addition to that, there will be scale symmetry, which says x mu goes to lambda x mu. And then there is another type of symmetry called special conformal symmetry. This form, I mean, we can write this down and we will write it later. It's a bit cumbersome. So let me just, for the sake of introduction, mention that these 4 types of transformation make what we call the conformal symmetry. So in particular, these symmetries, the group generated by rotations and translations and rotations, are a subgroup of this conformal symmetry. Okay. Now, why talk about this symmetry in particular? Well, this symmetry is quite powerful. So it turns out, so for example, in our real world, if you just have translations or rotations, there are a variety of things that could happen. Is there some fan or something? AC? Sweating like pig.
Can be done with it, but it's on.
Okay, it's fine. I'll just. Yeah. So. As I said, this symmetry appears in physical setting while describing various types of materials at their critical points. So I don't know whether you can sympathize with this motivation, because this is really, how a physicist would go about it. If you want to study something, you would ask, why should I study it? And the reason is because there are physical systems which realize this symmetry. So you have conformal symmetry, for example, that is the symmetry that appears when there is some material at the critical point. So you all know water. And water has 3 phases: liquid, solid, and vapor. And at a certain point in this phase diagram, when you tune pressure and temperature to be certain values, you get to what is known as the critical point of water. So in addition to translations and rotations, which are anyway present, you get the symmetry gets enhanced to this full-fledged conformal symmetry. Okay. And at that point, if you measure certain quantities, such as specific heat, with respect to the temperature away from the critical point, you get a power law type of behavior, with power being some very weird number, which is, I forget now, 114, some number like that. Okay, some very specific number that you can measure in an experiment. On the other hand, you can consider a different type of system, namely magnets. And in magnets also, you can play with their phases. The spins get aligned, they magnetize or demagnetize. So you can play with the external magnetic field or the temperature, and again, tune it so that you reach what is called the critical point, where there is scale invariance. Okay, and there also you measure certain quantities, and lo and behold, you get the same number. Okay, now how can that possibly be? Because at the heart, what makes water and what makes magnets are totally different things. But finally, the system is described by the same type of physical laws. In fact, even these numbers that come out, this is just one number, but there is a series of numbers, a sequence of numbers that just matches for these 2 systems at critical points. So the lesson of me telling you this is that this conformal symmetry is so powerful that not only it just says that the vectors should be organized according to the representations, which is what a symmetry would just tell you if you study its representations, but it constrains the dynamics also. And so it goes towards, in great lengths towards describing the system completely. Okay, so this is one motivation to study conformal symmetry. Another motivation is when you have so in the recent times, from string theory, we know that theories of quantum gravity are also described by conformal field theories. Okay, so this is something that I will not go in any detail about. But this is the so-called ADS CFT correspondence, where a conform field theory, meaning a particular type of system with conformal symmetry, describes. Thanks a lot. Describes quantum gravity, and quantum gravity is a holy grail for physicists. So that's all the more motivation why we study conformal symmetry. And yet another motivation, it is now more of a from a mathematical point of view, is that in recent times this symmetry has been used to study a spectrum of Laplacian on hyperbolic manifolds. Okay, so you write down certain equations which follows just from symmetry, and you use certain positivity coming from positivity of norms of states, which is what we call unitarity sometimes. And this gives you a problem, and you which ends up, this positivity ends up putting bounds on the eigenvalues of Laplacian, and these bounds are now very good, in fact better than some of the bounds that mathematicians have been able to write using other techniques.
How recent are these bounds?
So these are quite recent. Shrideep has played an important role in it. I think a couple of years. And then experts in this field like Sarnak, etc., they are quite interested in that, is what I hear. So this is just some words of motivation of why we study conformal symmetries. Now supersymmetry. So this is the motivation for conformal symmetry. Now, what is superconformal symmetry? Now, so supersymmetry, as I said, is a different type of symmetry. This is not like this symmetry that I just talked about, which is translations, rotations, or scale. This symmetry has the weird property that it squares to itself. So instead of the Lie algebra being formed by commutators, so whenever you write down a particular Lie algebra corresponding to some Lie group, you write down generators and their commutators, and you write an equation of this sort. Where these are the structure constants, and this is a commutator thought of as SI Sj minus Sj Si. Right. So supersymmetries are not symmetries of this kind, but rather they are given by anticommutators. They are described by anticommutators. Okay. In particular, a generator just squares to 0. A given generator just squares to 0. And why, as a physicist, you would be interested in that is a little bit of a difficult topic to get into right now. But just to say some words, it relates what is called a boson to fermions. Okay, these words may not make much sense now, but it's a different type of symmetry. That's the end of it. And now what you can do is you can enhance this or extend this conformal symmetries with supersymmetry to get what is called the superconformal symmetries. And these symmetries have also played an important role in string theory. And a lot can be said about these superconformal symmetries. In particular, there are various non-trivial dualities of describing, so there is a particular system that describes physics at one coupling or okay, so this is also a little bit difficult to explain now, but sorry, what is an anticommutator? It's this with the plus sign in the middle. So by anticommutator, I mean this.
Then the overall thing is not Lie algebra.
It's not Lie algebra. It's Lie superalgebra.
It's a well-defined structure.
Yeah, it's a well-defined structure. Mathematicians do study it. Yeah. But it doesn't fit in the ordinary Lie theory.
But there are classifications for those similar to the Cartan classification.
Yes.
They have some base space, which is an ordinary Lie algebra. So you can project from that by forgetting these generators. You can
You can just focus. So you can look at the superconformal symmetry and focus only on the bosonic generators, meaning the generators which don't have. So the superconformal symmetry will have both generators which have ordinary Lie algebra structure and also the super generators which have this anticommutator structure.
Maybe mathematicians are more familiar with the term even generators and
odd generators. Even generators and odd generators. Graded algebra. Yeah, exactly.
So this Lie algebra, does it represent something in the geometry?
The super algebra?
Like the Lie algebra would be something like a
tangent space to the Lie group.
What would be the counterpart of super algebra?
Yeah, so that also is describing some tangent space. I mean, it's mostly algebra. One does not talk about supergroups. I don't know whether there is a
Let's
version.
talk about supergroups.
Yeah.
There's quite a lot of thing about study of supergroups as well.
Hmm.
I think they are graded manifolds. So manifolds which are not, which don't whose coordinates, if you like, are not ordinary. Not all of them are ordinary C numbers, but they can be thought as fiber bundles over an ordinary manifold. So I think a supergroup manifold is generally a bundle over the corresponding ordinary group manifold.
I don't know
Bundle
about
has
the global
something-
structure. I don't know about the global structure, but at least in the tangent space, it's just an extension of the ordinary Lie algebra with these odd generators. There is a geometric significance to it also along these lines.
They're not real or complex numbers, but they are
The square to 0. So this superconformal theories, I mean, systems with superconformal symmetries also have played an important role in string theory, especially in establishing various types of non-trivial dualities, meaning a system is described by a particular variables, and another system, which is a totally different system, is described by the same variables, or the other way around. So that's why superconformal symmetries also are natural structures to study. So that I will do in the final lecture. Okay, so this is the motivation that I wanted to say so far about just the study of such symmetries. So what I will do now is get into just describing quantum field theories from integrals, as I said. So just so one is very familiar with integral of this sort. Okay, this is just a Gaussian integral. Anyone can do it. Now, if I add to this some term like this with lambda positive, I require this to be a positive quantity so that this integral, or rather quantity that is bounded from below, so that this integral is convergent. Okay, now this integral becomes a little difficult to compute, right? But if this lambda is small, what you would do, you can expand this in lambda and write it as a 1 plus lambda x to the 4 2 factorial. And in this way, you can compute this integral, right? Very simple. Now, so let's just call what is written here as some function s of x. As I said, this is a bounded function. So now, in addition to computing these integrals, one can compute the moments. So for example, one can compute quantities of this type. So let's define this as expectation value of x to the n. Okay.
maybe after dividing by the same thing, right? Without the x to the n.
No, just a part of definition. It doesn't matter much. Okay. So one can compute such things also. Now, as I said, if s of x is just a quadratic function of x, this is very easy to do. This is just a quadratic integral, a Gaussian integral. But if you have some other complicated things like lambda x to the 4, etc., this would be a bit difficult to do, and you would have to do you have to use the series approach, which in physics sometimes called perturbation theory. So you just have order by order expansion in lambda, and for every power of lambda you can compute the answer. But let's say, even though you don't know this s of x, but you know that, yes.
There, when you said that you are expanding the your minus lambda x square 4, lambda has not to be small to expand, because exponential series is always converging for finite value of lambda, right? Like if we see from that example.
Yes.
I think he's saying it need not
It need not be small, but if you want to actually do the calculation, in physics, you know that you compute first few terms of this series, and you take it as a good approximation to the answer. But that will only be true if lambda is small, right? I agree that if you keep this full series, then that's a perfectly fine thing to do. But if I want to truncate this series and pick first few terms, that is a good approximation only if lambda is small. And that's what I mean. Now, let's say you don't quite know what this s of x is. This could be a complicated function, but let's say it obeys this property. S of x is equal to minus s of minus x. Okay, which is the case, for example, for this integrand. Okay, so in addition, in other words, this is a symmetry of s. X going to minus x is a symmetry of s. It's an invariance. Okay, now if I have that, then I immediately know x to the power any odd number would be 0, right? Because you can simply change x is a dummy variable, you can change x to minus x, and you get this guy is equal to minus the same guy, and that will give you 0. Okay, so in this sense, this is an extremely simple example of how just having a particular invariance will let you constrain these expectation values that you insert here in the integral. Okay. Now you can consider a more sophisticated example. So let's consider multiple variables. So this is not an integral over a single variable x, but let's say multiple variables xi. I goes from 1 to n, let's say. Okay, and you have e to the power minus s of xi. So this is a function of I variables. And what kind of function is this? Well, it could be any function, but let's take it to be like this. Okay, some function like this. Well, okay, so first forget this term to begin with. Let's just take these two terms. Okay, this is just a separate integral for each x, and what I said earlier holds. But now, what if you have this? Now, one immediate thing that you can realize from this expression is that you have the following symmetry of s. So this is a function of all the xi's, so I can write it as x1, x2, xn, and this is equal to s of x2, x3, okay. Here I should say that I have identified xi, xn plus 1 to x1. Okay, so just when I shift, so if I shift I to I plus k, this s remains invariant. That's the property of this. So as a result, if you compute xi, xj, it will only depend on I minus j. Is this clear? Meaning if I compute x1, x4, this is the same as x2, x5. And this you can change by just doing this change of variables. x1, x2, x3, 2, x2, x3. So, okay, if we do change of variables, you will see that these two are the same. Or more generally, this expectation value of xi, xj just depends on I minus j. Okay, so this is just an immediate consequence of the symmetry of the action. Now, what role does this play? Does this term play? You see, this, because this is a weight that is a damping weight, it is costly for xi and xi plus 1 to be different from each other, right? This integral wants xi and xi plus 1 to be close to each other. As I said, in the absence of this term, x at one place, x1 and x2, they don't have anything to do with each other. But because of this term, x1 and x2, they want to be close to each other. Okay, so in some sense, x1 and x2 are close to each other, just because 1 and 2 are close to each other. So this is what we call locality. Okay, so x given by the index 1 and x given by the index 2, they like to be equal to each other. So if you want to think of these x's as some sort of a function defined with, so this is my I space, this is the index space, so I is equal to 1, 2, 3, 4, 5, and the x could be any value here, this x1 could be value here, x2 could be value here, and so on. So what this term does is that it makes sure that these two values, they don't differ too much from each other. Okay, so the configurations of x that contribute to this integral heavily are the ones that are smoothly varying as you change I. Okay, I mean, it's a discrete label, but you see what I mean, that as you go from I to I plus 1, you don't want to change x too much. If you do, then that's a heavy price to pay in the integral. Okay, so this is a property that one likes in physics. This is called locality. It tells you that the index I and I plus 1 are really next to each other. Okay, and this is the idea that you promote. So this is basically the idea that lets you promote this, promote I to a continuous variable. We'll call this t. So previously we had an integral of this sort, product over I, x of I. This was a subscript, but let me just write it as a function of I, e to the power minus s of x of I. So now what we will do is we will promote this I to a continuous label. So this integral will become product over t, x of t, e to the minus s of x of t. So it may seem like I haven't done much, and indeed I have not. I've simply taken this index space here, 1, 2, 3, 4, and I've just promoted to a straight line, which is labeled by this coordinate t. Is this clear? Okay, and then this term here, what does this become? When I promote I to a continuous variable, what term would this become? This would be a derivative term, a derivative squared term, right? So if I were to just map what the s that I wrote down to this continuous language, then this s of x of t would simply be d by dt of x of t whole squared plus kx squared plus lambda x to the 4. Yes. Yeah, just once again. dt.
I think you meant dx of t.
Like that?
In the line above also, don't you want the product dx of t rather than x of t?
Here?
Yeah.
Yes. Correct. So this sum over index that we had, sum over I, it becomes integral over t, right? And xi minus xi plus 1 whole square, this becomes this derivative term. And here these are just unaffected because those were just product at a given index I, right? But now this has a nice picture because what we are integrating over are all x's, is now our functions. So this is a functional integral. This is a functional integral. So far we were talking about finite dimensional integrals, but here we promoted to an infinite dimensional integral. Now, of course, one has to make sense of these types of integrals, because these integrals usually are plagued with divergences, and one has to be very clear treating those. And that really is the meat of quantum field theory, which we will not get into. These are we'll just talk about bones of the quantum field theory, not the meat. So we will not talk about how to properly understand these divergences and how to remove them and so on. But at a formal level, one can write down this type of an integral, which is an infinite dimensional functional integral. So now we can talk about symmetries of that. Exactly. So indeed, you have x going to x plus alpha, where alpha is any real number, is a symmetry of this, because this derivative is unaffected, right? And these because of this dt integral, you can just simply change the variables and get back the same integral.
No, it's not symmetric under x goes to x.
Sorry, t goes. Yeah, I meant t. So actually, to be totally clear, I should write it as x of t, because that's the integration variable, goes to x of t plus alpha, right? But sometimes we use this shorthand notation where instead of changing the variable, we just change the index. So t at this stage is just an index, that the role, it just plays the role that of I that we had before. So we just represent this transformation as just the transformation on the index space, t going to t plus alpha. Okay, and this is a symmetry. And as a result, if you were to compute xt1, xt2, this is just going to be a function of t1 minus t2. Yes? Okay. Now there's certain more points that I want to make about this integral. In fact, yeah, we can already talk about the difference between classical and quantum theories. So okay. So imagine that there is some constant here, 1 by h bar, okay, that is in front of this action. So I just scaled this action. And now let's take the limit that h bar goes to 0. What will happen? This weight is going to increase, okay, and this integral will be dominated by what is called the saddle point, right? So saddle point is nothing but d by dx of t of s of x of t equal to 0, right? So if you write down what this is a functional derivative of s of x of t by x of t, and you would get x okay, I'm not careful with the various factors, because you would get some 3 factorial and such. But okay, so this is the kind of equation you will get, right? So for now, let's just ignore this term. Let's set lambda equal to 0. Now you have this, and what is this? So from your school days, this is just telling us that this second derivative of x. So if you now think of x as a position in some space labeled by t, then the second derivative is what we call the acceleration, right? So this is the acceleration is equal to kx. So acceleration is proportional to x. Okay, this is what is this equation describes the spring. So you remember this kind of picture. in your school days, where you have the spring and this mass. This spring has a constant, spring constant k, right? Spring constant k, and now this you move this mass around, and this mass exactly obeys this equation of motion, that its acceleration is proportional to how much you stretch the spring. Okay, so already just by starting with some finite dimensional integrals, we are in a position to describe a classical motion of this mass attached to a spring, or in other words, a particle in a harmonic potential. Okay, so this is giving us an oscillatory motion. But now this is in the limit h bar going to 0. But what if h bar is not 0? Well, that means that it's not true. Sorry. Minus kx. Yes, I guess it should be minus kx. Here? Okay, sorry. But this is A only, right? Okay. Yeah, sorry. Fine. Good. Yeah, so but now what if h bar is not quite 0? This is the picture that you would obtain when h bar is 0, very close to 0, that the integral will be totally dominated by the trajectory of the particle x of t moving according to this equation. Okay, but when it is not 0, that means there are other trajectories, meaning other functions x of t, which don't quite oscillate given by this equation. They also contribute to this integral, right? But less. This is the trajectory that contributes the most, and the other trajectories contribute less and less and less as they are further and further away from this equation. So this is basically the essence of quantum mechanics, of Feynman's sum over histories interpretation of quantum mechanics. So in order to understand the classical motion of the particle, we just see that particle is oscillating like this. But quantum mechanics is about quantum mechanics says that for any finite value of h bar, this is not what will happen, but rather all the trajectories will contribute. Okay, so that's what leads to this double slit experiment. For example, you have these slits here, and there's some source here, and you have a screen here. The particle can go like this, and the particle can go like this, and you have to sum over them. Okay, so this introduces a new structure, namely structure of the vector space into the problem. Previously, there was no vector space. It was just the trajectories of particles. But now you can add these trajectories because this integral tells you to add them. Okay, so the message is that for any non-zero value of h bar, this is describing a quantum particle and not a classical particle. And the h bar going to zero limit, it becomes more and more like a classical particle. Okay. Now, where are the states here? So let's describe that. So let's say there is some. So let me denote this time by this axis time, and this x of t, which is the functions, the space of functions on which we are doing the integral, as some function like this. Okay. Now what we will do is at certain point t naught, we will impose the boundary condition that x is x naught. X of t naught is x naught. Okay. So now let's write down this integral again with this boundary condition imposed. So you have integral dx of t like this, right? And you impose that at x of t naught, this is x naught. Now, the thing that I get is some function of x naught, right? Because that's the boundary condition on this. And this function is what we call the wave function, and describes the state of the system, a vector or the state of the system. Is this clear? So from an abstract point of view, what is just what is happening is that this type of integrals, they naturally define a vector space on this normalizable functions on X, this psi of X naught. So these are what we call the wave functions. Now, this picture also lets us define what we call the local operators. So as I said, we can compute such things, x of t1, x of t2, or even d by dt of x, d by dt of t squared. So you can insert any of these variables inside the integrals and aim to compute such a n-point function, let's say. So when we have n such objects inserted, we call this n-point function. Now we can understand that each of these terms, each of these insertions can be understood as an operator, and it's in the following way. So you have this integral, doesn't have any boundary conditions in the past, but so let me just pick this one and try to describe it as an operator. So this, as I said, gives you some wave function psi of x naught, okay, which is the boundary condition given at t1. Now what I do is, instead of this, let me compute. So this is like, you can think of it as this is the t, and you are imposing this boundary condition with a particular value of the coordinate x naught, and that's what is defining psi of x naught for you. But now what let's do, let's take t to be a little bit bigger, so by a small epsilon amount, and again put the same boundary conditions x naught, and insert this x of t here. So in other words, what I'm doing is, you have x of t1 is equal to x naught, again the same exact thing, except that I'm going to write down x of t1, or for that matter, any function of x. So let's call it O of t1. Okay, so this could be x, or it's a derivative, so on. And this will give you a different state, psi prime of x naught. Yes, because of this insertion. So in that sense, you can think of this as an operator defined locally at point t1, because it can change the state of the system from psi of x naught to psi prime of x naught. That's in that. This is the sense in which this is an operator. Okay, you can express that in the basis of these functions on this in the functions on x naught by imposing boundary conditions on two sides. So you can impose x of t1 is equal to x naught, and x of t1 plus epsilon is equal to x naught prime. And this will give you a kernel which depends on x naught as well as x naught prime. So this is basically an expression for this operator in the x naught basis. So you can write psi of x naught, psi prime of x naught is equal to integral d x naught prime k x naught prime psi of. Okay. So this defines you and explicitly how this insertion can be thought of as an operator on the Hilbert space, on the vector space. Is this clear?
But x naught prime is required to be infinitesimally close to x naught, or it can be part.
No, infinitesimally close. If you want to define a local operator.
So then the integral of x over x naught prime doesn't have a much of a range.
Yeah. That's right.
I mean, if it's infinitesimal, you don't even do the integral; you just multiply. I mean, this is just equal to epsilon times whatever the integral, right?
Yeah. But I mean, in general, you could even take it to be, if you don't want O of T1, but rather, I mean, this epsilon can be anything you want to define the operator. But in order to define the local operator, you would want to take that limit. You are saying that there's only one, but there is still some integral to do, right? At a particular value T1.
Yeah, no, I mean the lower integral, this integral of dx naught prime. That doesn't seem to have much of a range, right? Because x naught prime is just epsilon away from x naught.
No, T is epsilon away from x. T is
epsilon away from from T1.
Yes.
And so x naught prime is epsilon times x prime of T1 away from x naught.
No. These boundary conditions are up to me. I can put them to be any boundary condition I want.
But if this is a continuous, is it a continuous function? X of T1 plus epsilon.
Yeah, I mean it is given by this weight.
I can write it as x of T1 plus epsilon x prime of T1. The upper limit of this integral, x of T1 plus epsilon.
Yeah.
That is x of T1 plus epsilon x prime of T1 plus terms which I drop because epsilon is infinite.
Yeah.
So then x naught prime is just epsilon x prime T1 away from x naught. So it's still infinitesimally away. So this boxed integral you are doing, that's what I'm puzzled, because there's the limit to epsilon is really infinitesimal. There shouldn't be any integral.
Yeah, I mean these functions need not be. I mean they need not be. That x naught prime need not be very close to x naught.
Okay. So then we're not dealing with integral over differentiable functions.
I mean that whatever that is will be given by this kernel K. The weight associated to this x naught being far away from x naught prime will be given by K. So this kernel, in other words, what you're saying is this kernel is peaked at delta function.
Yeah,
which is true. Okay. Fine. So what we did is to promote this index I to T and defined integrals on these functions. We saw how this functional integral can have symmetries, which are xt going to x of t plus alpha, or simply t going to t plus alpha. And we saw how it can help us define a state using the integral and also operators on this. I mean, the vector space, let's say. Okay. So this is what we call quantum mechanics. Because the functions that we are integrating over x of t are functions of a single variable. In quantum field theory, what we do is we extend this t. T, remember, in the original integral was just an index space. And this index space has been promoted to a real line. But now instead of one real line, there could be two real lines. I mean, it could be R2, right? So this t is promoted to some point on any manifold M, some d-dimensional manifold M. Okay, and you can define this instead of x. Let me call these functions phi of x. So change this. Note the change in notation a little bit. This point on this manifold, d-dimensional manifold, I'm denoting this as some x. Okay, this is not the function anymore, but rather the point. So this is what the index becomes, x. And this function, which was x before, is called phi. Okay, so now in quantum field theory, one talks about functions defined on manifolds, phi of x. The x is a point of the manifold. And again, same story. You have to write down this integral. And interesting things that you can compute with this integral are, again, ones where you insert various functions of this phi. So you could have phi of x1, phi of x2, derivatives of phi of x3, their squares, and so on. Okay, so these are what we call the correlation functions. So let's call this as O1 of x, O2 of x. And as we described earlier, these can be thought of as local operators. So this type of integral will define correlation function of this sort. Okay, and these are the primary objects that one is interested in formal quantum field theory. At least this is clear, right? This is just, this is a infinite dimensional integral, so one would have to deal with infinities, but formally this defines a set of such functions that we call observables or correlation functions. Now, when S of phi of x is quadratic in phi of x, it's a Gaussian integral. Okay, so even though it's infinite dimensional, because it's Gaussian, it can be performed. And you can compute these things explicitly and exactly. But when S of phi of x is not quadratic, and sometimes we don't even know what it is, then you cannot quite do that. And you need other methods. As I said, if the non-quadratic pieces are small, you could do perturbation theory. You can expand those pieces, right? And approximate the full answer by some terms in that series. And this is what is known as the Feynman diagram expansion of these correlators.
So don't you want to be like originally we wanted as a sequence of things to be impose a condition, right?
Yeah, so you're talking about these boundary conditions that I was talking.
Originally you took x1, x2, xn, and so on.
I think those x's are not these. This is like the T that we have prepared. These x's are like T1, T2, T3.
Oh, I see. Yeah, so as I said here, so when we went from this quantum mechanics to quantum field theory, this what we had T, what the variable
Yes, and then
T had become x, and this phi x has become phi.
so what is in this sequence?
X1, X2, X3, they're just arbitrary
Points. These are arbitrary points in this manifold M.
It's like moments. You're calculating some moments with respect to this method, and then you just insert the thing with moment you want at anywhere you like. So it's not a sequence in the sense there need not be any more x's.
So these x1, x2, x3 are just arbitrary points on the manifold, and you are inserting this theta or O. Actually, I was calling this O is any function of phi, but it's evaluated at that point x1. So it could be phi of x1 or phi square of x1, or it could also involve derivatives. So the general notation I'm using I'm using for that is just O of x. So there's an O1 of x, O1 of x1, O2 of x2, O3 of x3, which I can just insert in the integral and try to compute those objects, which are called correlation functions in physics. Now this probably when you say, yeah, exactly, where is the locality coming in? Maybe that's what you're saying. You know, how do I know that this integral over functions, so this is the integral functions on the manifold, how is it that it is dominated by functions that do not vary very fast, do not vary at very small scales, right? Otherwise, you know, each point will be independent and the values of the functions will do whatever they want. That's because this S of phi of x does have the derivative squared piece, which suppresses all the contribution, you know, contribution coming from functions which vary very fast. So what kind of term is that? Well, it is, you take a derivative, you take a gradient. So that usually we write it as d mu of phi of x, right? And you take its magnitude. So if you have this term in this S of x, then that would suppress very fast variations of phi. This is what gives you locality.
Phi is seen as a local coordinate or something.
Phi is some function. Phi is a function. Coordinate on what? No, x is the coordinate. Phi is a function on the manifold.
So it's not an integral over the manifold, right? This is an integral over the space of functions on the manifold.
Why you want to treat very locally on the point x? X is a point on the manifold, right?
X is a point on the manifold, yes.
Phi is a local function on the manifold. So
Phi is a function.
It's not local. This is phi. I mean, phi of x is just a function on the manifold, right? It takes a value everywhere on the manifold.
Yeah. So phi of x, by that, phi of x1, one just takes that particular, you know, one is integrating over the space of functions. So you take one particular function, evaluate its value at x1. That's what you put in the integral. And then you integrate over all such functions by taking those values, phi of x1, phi of x2, and all that.
I mean, if you take a, in particular, it can be local, you know, local coordinate. So you take a local chart and then phi can be a local coordinate.
Well, phi just a complex function. So it's a function. It's a function from MD to.
There is a local chart, but phi is the space of functions, right? And functions don't have to be invertible. Phi is not a space of. Phi is not in the space of invertible.
Phi is, yeah, from this, yeah, so M to R, right? So
M to R or M to C.
Yeah, that's fine.
Yeah, but it could be any kind of function. There's no restriction on what.
Okay. It's on the full.
Yeah. Okay. So this kind of integral also lets us define the Hilbert space as we defined in quantum mechanics. And that to do that, what we can do is let's say take a particular ball from this manifold. So this is some ball inside MD. And on this ball, on the boundary, you impose some condition that this phi is some finite of x. Okay. On the boundary, you fix this boundary condition and then do the integral. And with this boundary condition and integral, it will define for you some state psi, which is a functional of phi naught of x. So in this sense, a Hilbert space is attached to a boundary of MD. Okay. And again, one can define local operators by basically inserting this operator somewhere in this shell and doing this integral. So more explicitly, what you can do is you can just define the path integral on a thin shell and put phi naught of x1, phi naught of x as boundary condition on this inside shell, and on the outside shell you put, let's say, phi1 of x, and then do the path integral on this shell. By path integral, I mean this integral functions, and this gives you a kernel which depends on phi naught of x and phi1 of x. And you can have some operator inserted here, for example, and this will give you an explicit presentation for that operator, local operator. So in particular, note that any local operator will define a state. And to do that, instead of the shell, what we do is we again do the integral of the ball, but insert a local operator O of x at the origin. And this, and again, fix this boundary condition to be phi naught of x. And the functional that you get will be the state associated to this operator. Okay, so there is a map from any local operator to a state. Now in conformal field theories, we will see that there is a map in the reverse direction also. Given a state, there is a map to a local operator, which is what gives us a lot of mileage in dealing with conformal field theories. And this is called the state operator correspondence. It doesn't exist for general quantum field theories, but for conformal field theories, there is a very canonical map from a state to an operator, which is a very different, weird thing. If you have in finite dimensional cases, you don't expect there to be map between operators. So given an operator, you can construct a state in some way because you can fix some initial vector, and operator acting on that will give you some state. So there is, in some sense, you can consider this type of a homomorphic or whatever homomorphic map from operator to the vector space. But given a state, there is no natural operator that you can construct from that state. But in conformal field theories, in that sense, are powerful because given a state, you can construct a canonical operator.
Okay, so here's a question. Supposing I had a simple system like harmonic oscillator, which is not a conformal theory. Given a state of the harmonic oscillator, can't I define an operator to be that operator which acting on the vacuum gives me that state?
No, many such.
There are
many such.
That's the problem. So
Yeah.
the only in conformal
Because you just make sure that you can multiply that operator by an operator which doesn't do that, doesn't do anything in that direction. It can rotate the other directions.
Correct. Or for example, I could add to an operator any annihilation operator which would just annihilate.
Yeah, exactly.
And it would, so uniqueness is key.
Yeah. Okay. Good. Any questions so far?
One comment, if I can.
Hmm.
You gave a very nice description of definition of state in a Hilbert space and an operator. But maybe it would help to have also introduce the norm in the Hilbert space, which you do by doing the path integral
Yeah.
to complementary space.
Exactly. Yeah, I was just about to.
But that requires again for you to normalize the path integrals which have not been wanting to do.
Well, but as far as the sign of the norm is concerned, because that's the main
Sign.
thing, that is sign, whether it's positive or negative.
Yeah. What about
I mean, we will only be using the sign of the norm. That
No,
be
but
interested in positive norm
conceptually,
states.
the fact that you have got a Hilbert space structure
Yeah.
comes with a norm. Actually,
Yeah.
comes with a norm. So
Yeah.
that's a nice thing to
Right.
do
Exactly.
in the path integral.
Exactly. Yeah.
Actually, not many textbooks do it, for example.
Mm.
Either norm or even the state, this kind
Yeah.
of definition.
Right. Yeah. So let me just elaborate on what Sunil was saying.
What does the manifold mean? In physical terms, what does the manifold mean?
In physical terms, it's literally the space in which we are doing physics. So in this case, for example, the manifold would be R3, given by the x coordinate, y coordinate, z coordinate. So it's really the manifold. So this MD is basically just R3 in this case. But of course, there is yet another aspect to this story that I have not emphasized, namely time. So this is not our space. Is a point in the space is given by x1, x2, x3, or x, y, z. But there is, of course, a time coordinate also, right? So that's an extra direction. That's the fourth direction, time. But that has a different status compared to the other three directions. And mathematically, the way to say it is that the physical space is not quite R3, but R3 comma 1. Okay, Minkowski space. So here in R3, the symmetry transformations, the rotation transformations are the ones that keep the form 1, 1, 1 fixed, right? That's why you have orthogonal transformations, and those corresponds to rotation. But in R3 comma 1, you have to the symmetry transformations are the ones that fix the form -1, 1, 1, 1, 1 on the diagonal, right? And this gives you the SO 1 comma 3 as symmetries, and this basically is nothing but special relativity. That if you write down explicitly what these transformations are, you would get what are known as Lorentz transformations, having to do with frames moving with some speed. So that corresponds to the rotation between time and space. So to long story short, the space, this MD that we are, I mean, from a physical point of view, is just basically the space in which we are working. For now, for the purposes of this talk, I'm taking that space to be totally Euclidean without any -1 in the signature of the metric. But you could have a -1 in the signature of the metric, in which case that -1 direction will play the role of time.
So time is some special axis, or it's on the same footing?
It's on the same footing. It just has a minus sign in the signature of the metric.
Transmission invariance and all.
Yeah. So you can also talk about time translation invariance.
Okay.
That's also there. Just like the translations in space, you expect in translations in time to be a symmetry of the theory. Yeah. And also rotations, as I said. So there is a rotation. So here, when we move in XY plane, X and Y directions are mixed together, right? So new X is a linear combination of this X and this Y. So similarly, you can talk about transformations which mix space and time. But their interpretation from physical point of view is not some rotation, but rather boost. We call it boost, meaning, moving with a certain speed. So even in in physical terms, you say that if you do an experiment here or you do an experiment in a train, it should be the same, as long as train is not accelerating; it's moving at a constant speed. So that corresponds to, if you think about these transformations, actually a rotation between space and time. Yeah. So, but for these purposes, I have not focused on that aspect. I have just taken this manifold to be Euclidean manifold. Meaning its metric just has a positive signature. In fact, I have been saying manifold, but I'm just interested in that space being just RD, some d-dimensional flat space, RD, with the metric being just 1, 1, 1, 1, 1. Nothing fancy. Okay, so that's what we will take. MD is just going to be RD. Or one could also take SD, a sphere, a d-dimensional sphere. In fact, to define the norm that Sunil was talking about, it's actually convenient to work on SD. So you have SD, and then you cut it along the equator, right? And this gives you a hemisphere. Let's say southern hemisphere and northern hemisphere. And you can impose a particular boundary conditions at the equator and do the path integral over the southern hemisphere, and that gives you a state psi of phi of x naught. And similarly, if you do so on the northern hemisphere, you get the state in the dual space. And that's because there is a map from space and the dual space to a real number, namely just, you glue these together, these two hemispheres together, and you integrate over these boundary conditions. So let's say this gives you some psi hat of phi of x naught. And the way I will make a number out of this, the norm out of this, is integral d phi of x naught okay, and this is nothing but the full path integral over the entire space, which will just give me a number. So in this sense, this
inside the SD by compactification, right?
Yes.
So what does the equator mean?
But in RD,
Yes.
yeah, in RD you can,
Image of RD in SD. What does the equator
yeah, that is just this unit sphere.
Yeah, but in physical terms, what does the equator mean?
In SD? In SD, you mean?
No, in the equator of the SD.
Yeah.
What
So
was it
equator
in
of
R?
SD is SD minus 1. That's what I mean by the equator.
I'm not talking in mathematical terms.
Yeah.
You're taking this space time and embedding it into SD.
Not embedding, compacted.
It's compactly fine, but it's RD is not compact. So you have to.
Yeah.
But what I
You
mean
have
is
to
that
point that
you have RD sitting inside SD. So what is the physical meaning of the equator?
Okay. So
For
first,
example, if you take R2, then the circle, the unit circle in R2 is the equator when I make from R2, I make the Riemann sphere. Is the analog of that.
Yes, but I'm just trying to understand what.
That's right.
yeah, but a priori, I mean, there need not be any relation between the integral, functional integral that we define over RD and the functional integral that we define over SD. A priori, there is no relation between the two. But it is true that for the conformal, the theories with conformal symmetry, there is indeed a relation. And you can map one to the other using this stereographic projection. So stereographic projection will give you an explicit map from SD to RD. And if you see where the equator goes, it just goes to the unit sphere in RD.
So it's some distinguished point where set of points, right? So what does distinguished set of points?
No, it's not quite distinguished. It comes with a choice of origin. So you pick an origin for RD, and then the unit sphere would be the equator.
So what happens at the transition point in physical time?
No, nothing special happens. Nothing special.
I think on the sphere, the equator is just a way of separating one half from the other half. The natural choice.
And it's reflection symmetric, meaning
some suitable metric on R2, the unit circle does the same. To separate the interior of the disk by this inversion map is projected to the exterior of a disk.
maybe that's another way to say it, that
stereographic projection.
Inversion, there is this inversion that you can do. X mu going to x mu divided by x squared, mod x squared. That its fundamental domain is just the unit sphere. And it is the outside of it is related to the unit sphere by inversion.
But when you realize RD in SD, you have to make the choice of a point, and then there will be a notion of an equator. Somewhat.
There will be or there won't be?
There will be.
Yeah. Yeah, so you do have to make a choice of origin, for example.
And you.
Okay. Okay. So here I just wanted to let you know how one would compute the norm of states. So if you have a state, so you can think of, as I said, you can think of the state as a path integral over the southern hemisphere. And you can create it with any operator insertion of x. And this will give you a functional of these boundary conditions. And that's a state vector. And if you want to compute the norm of this state, what you do is you take the northern hemisphere, exactly insert the same operator at the opposite point. It's mirror reflection. And then do the integral here. That will give you its dual state. And the norm would just be the full integral on this sphere. Okay.
Divided by the one without the
divided by the yeah. Okay. So now let's look at the symmetries. So as I said, for us, MD will be RD. And let us write down this integral again. And this S is actually a local integral. Okay, so and this is called the Lagrangian density. So this is a function of the field and its derivative. Okay, so this is the structure that physical theory has for this action. This S is called the action. Okay, and now we can, so for example, let's take for concreteness this L to be okay. So all of this has x coordinate, which I've suppressed. And in this theory, let's compute phi of x1, phi of x2. Now, as we discussed, this does have a translational symmetry, which is clear from this, which says phi of x mu going to phi of x mu plus a mu is the symmetry of this S, right? Because of this integral. This integral makes these two terms invariant and this term also invariant separately. So all the terms are separately translation invariant. So as a result, we know that this, whatever this is, should be a function of x1 minus x2. Not depend x1 and x2 separately, but rather only a function of x1 minus x2. So this is the consequence of translational symmetry. So we can talk about infinitesimal generators also. Sorry, what? Yeah. Yeah. That's what I was thinking. Yeah. I think this is probably a natural stopping point. We can continue later.
Okay. I mean, if you had something small to say.
No, I think this is anyway a good point to stop.
Okay.
Yeah.
Any questions? You can also ask questions in the next.
Yeah, sure. Exactly. So so from more formal point of view, that's what a quantum field theory is. What?
I wanted to ask how states and operators.
Okay. Yes. Okay. So let's just talk about them directly in the case of the manifold. Okay. So these are the kind of integrals that we talked about.
And what is this product on a continuous?
Yes. So here you should think of this as an integral over the functions. And this tells you that you can think of it as integral over the value of the function at separate points. So previously when you have multiple x's, how did you write down the measure? So you write dx1, dx2, dx3, right? So this, another way to write it is x of I, dxi, and this, instead of the subscript, you can write it as this function I, right? What does that mean? That for a given I, you have a dx.
For finite,
So that's the magic that physicists do. So for even for continuous value of indices, first of all, continuous indices don't make sense. It's just some variable. You think of this measure as product over t x of dxt. So meaning at every value x, every value, at every point in t, you are doing an x integral. Here. So the way I define it, it seems like, all these integrals are separately defined, meaning at this point in t, this point in t, but that is not so because of the measure. The measure has this e to the minus, this derivative factor, right? d by dt x whole square, which tells you that when you do this integral, even though the measure, this dxt tells you that you are integrating over each t, you are doing a separate integral. This measure tells you that the value of x here and here should be very close to each other. Not very close to each other, but they cannot be discontinuous. The functions cannot be discontinuous. Because if it is discontinuous, this will go to infinity and not contribute to the path integral. So these are basically slowly varying functions dominate this integral.
But having said that, I think it's fair to say that there's no rigorous definition of product of dx of t.
Well, I mean, we work with it. So there's some
we do, but
definition.
without having a rigorous definition. I think that fact is important. As a result, actually, we can't calculate anything from first principle, not even in the simplest case, unless you divide out by the, that's why I was trying to emphasize dividing by the path integral, because only after you divide, you actually get any finite result. I don't think there's a single, even for a Gaussian of this kind, I don't think there's any finite answer. The reason it's useful in physics, at least my perception, you may disagree, is that you can agree by convention to fix this integral for one particular integrand, and then by ratios calculate it for all others, where some infinite factor which is buried in this murky definition of measure cancels.
So
Therefore,
Sunil
you
is
get
saying,
a lot of results, but not all results.
The family of names.
so Sunil is saying, instead of defining this, let's say, phi of x1, phi of x2, the way I did, as you define it by dividing this just without any insertions, just one. Okay. So as a result, the divergences that would appear here and here, you can make them cancel and get a finite answer for these things. So I suppressed this normalization in this discussion, but in physics we do normalize all these observables, all these correlation functions by dividing it with this integral where we don't have any insertions, we just have one. Okay. And now you were asking how to define the state, right? So what was the state? The state. Okay, I will directly define what a particular state is. So state would be some functions. Exactly. So on this MD, you can pick a sphere, let's say, and put the boundary conditions phi naught of x, some particular phi naught of x. As you are integrating over the functions on this ball, these boundary conditions is fixed once and for all, phi naught of x. And for each boundary, you will get some number, right? For each phi naught of x, you will get a number. So that will give you a functional from phi naught of x to a real number or a complex number, more generally. And that's what we call a state. And an operator, each boundary component will give you a vector space attached. There will be a vector space attached to it. So this is a particular state. If you do this integral, you will get a particular functional of phi naught of x. This will give a particular state. But to this boundary, that's not the only state. There are other states that you can construct. For example, inside this ball, you can insert phi of x. Just some operator, this local operator that I was talking about, right? But at the level of the integral, it's just a function value that you insert there. So in other words, we are doing, instead of doing this integral, you are now doing this integral with a phi of x1 inserted, some phi of x1 inserted here. So that's an insertion here in the path integral. Okay. Now, of course, the value of the integral will change because there is phi of x, and that will give you a different functional of phi naught of x. So that's a different state, again attached to the same boundary. So in this way, you can span the full Hilbert space by constructing states in various ways, by having these local operator insertions.
Okay.
It is time actually. Something.
Sorry, there's a remote question.
Sorry, yeah. Can you repeat the question?
Nothing. I was just setting time.
Sorry?
3 o'clock. For the next lecture?
Yeah, the next lecture is at 3 o'clock. So we are
Yeah,
going to.
3 o'clock.
Is that okay? I don't even know.
Hello, did you hear?
Yeah, I was just saying about time actually. So it would be to.
Devendra, can you say what? I'm not following what you're saying.
I'm saying it is time to for this lecture, right?
It's time to conclude the lecture.
Yeah, yeah.
Thank you.
Yes. Yes,
So
we are
the
going to
lecture is hereby concluded. Thanks. So these are all physics students.
Oh.
So there one math student is the one sitting there, and some remote audience.
Oh, I see.
Both on Zoom and on YouTube. So you have a few more people. But thank you. So 3 o'clock we'll start again. Come, let's go for lunch.
I'll go pick my son. So
Okay, go ahead.
see you at.